Hi everyone, welcome to the channel. If you're new here, what is on the channel is software engineering interview questions where I run through how I solve these problems and you are able to give me feedback, and yeah, that'll help me improve my content. And also I have supplementary materials on my website. My website will have breakdown of the source code specifically, and it'll explain what kind of mistakes I make as I do these questions in coding competitions, actual interviews, or when I am practicing. And my hope is that when I share these things, it will help you all improve. And yeah, I'll also have my GitHub where the full source code will be there. And yeah, both my website, YouTube channel, and GitHub will all contain content on how to use different various technologies. If this all sounds interesting or you've been following and you like what you have been seeing so far, yeah, please like this video and subscribe and follow me on social media. And please share it with anyone else that you think will find this useful. Without further ado, let's begin. So this problem is called parallel courses. We have n courses labeled from 1 to n, and we're given relations I, x, y, representing a prerequisite relationship between course x and course y. Course x has to be studied before the course y. In one semester, you can study any number of courses as long as you have studied all the prerequisites of the course you are studying. Return the minimum number of semesters needed to study all courses. If there's no way to study all the courses, return -1. So this type of problem I've seen before, and on LeetCode you can see other questions called, I believe it's called course scheduler, and so this can be done with topological sort. And don't worry if you don't remember how topological sort works and things like that. I think mainly what's important when solving these problems is recognizing patterns and being able to problem solve. Because what we can see is this, from this example, you can see there's this graph relationship, but even with the problem statement, we should, as we do more problems, of course, the graph representation is something that will jump to our minds. And we see that you could take as many courses with the minimum number of, take any courses as long as they're all the prerequisites are done. And so for that graph on the left with the 1, 2, 3, we can see that this is the course labeled 1, and the colon, what's after the colon is the in degrees. And I'll explain it in a moment after I put this. Okay, so in degrees, what it represents is the number of in degrees is the number of arrows or nodes that point to you. And if a number of node or arrow points to you, it means that those are the number of prerequisites that need to be completed before your course can be completed. So let's take an example. We say 1 has in degree 0, and this is the case because the edges are from 1 to 3 and 2 to 3, meaning that for 1 and 2, both with in degree 0, there's no prerequisites to take those classes since neither 1 nor 2 ends in the second position, whereas 3 ends in the second position twice, meaning that there are 2 prerequisites that need to be taken before you can take 3. And so if we have an array with all the in degree 0. So these are called sources. So a source is something that has in degree 0. It means that there are no prerequisites pointing to them. And so it's a great place to start because that's, if there's no prerequisites pointing to the node, we can of course take those classes. So as we process, we pop, and then the current node is now 1. And when we see the current node is 1, we check where the edge, we say, oh, if we completed 1, which other nodes does that mean the edge would decrease? Meaning, if I finish 1, does it solve potentially part of a prerequisite? And it does. So then 3 becomes in degree of 1. and then the current becomes 2 because it's the next on the source, and then we see, we see what edge 2 has, and 2 has an edge connecting to 3, so then 3 becomes 0. And then at this point, we know that 3 has an integer 0, so 3 has now become a source in that there's no longer any edges pointing to it. So then we put 3 on here. And then the current will be equal to 3, and then that will be processed. So one thing I left out was we need to keep track of the number of semesters. So we have semester here at 0, and at first we started with 1, 2. And so after we process this entire array, then the semester will get plus equals 1, and then the second wave of sources would be 3, and then it would be 2. So the answer is 2 semesters for that. So another example we have here is we have cycles. And so for the cycles, we see that 1 has 1 prerequisite, 3 has 1 prerequisite, and 2 has 1 prerequisite. And so when we have this case, we have an empty source, and we're not able to run our algorithm, which is good, because if we're unable to run our algorithm, we can check that none of the edges have been processed, and then we return -1. And so essentially, topological sort is kind of like breadth-first search in that we are processing all the nodes that have integer 0 first, and then continuing by expanding the next wave of nodes with 0 integers. If you would like more details on topological sort, please feel free to look that up and leave a comment below if you think it's if you think it helps to understand topological sort, or if there are any similar problems you think will help others understand. So one of the things, now we have the main idea, so I think it's good that we can write a little bit more comments so that we understand what we're writing when we code. So first things first is we need to make the graph structure. So create graph where key is the node and value is list of all nodes that can require, not can, but that require current node before completion. So what that would look like is if we had node 1, it would be an empty list, and then node 2, it would be an empty list, and then node 3, we would have 1, 2. And so we see sometimes there's an empty list, and so that's why it's good to use default dict. And so from collections, we will import default dict. And the values are essentially the edges, so we'll call this default dict. We'll make edges for default dict, and then we need to return the number of semesters, so make that 0. And then we also want to keep track of the integers. And remember, the integers was telling you how many nodes are, how many edges are pointing to that node. So 0 for these two, and then 2 for this. And so initially it will be 0. Well, it'll be 0 because we have not created the graph structure yet. Now, to create the graph structure, we go through the relations. As we go through each of the relations, the first node is the node that needs to be taken. So we say edges. That's a node that has a prereq. And then the list are the nodes once processed will decrement the integers for. So that's why we append the second as the value. And then we update integer because now we know that the every time you have an edge, the first node will now point to the second node, so the second node will have one extra in degree. All right, and then the next thing is place all sources onto source array, and this will help us do our DFS. And so we'll make a sources array, and then in range. We'll go through each of the nodes since we know that from the problem statement we have n courses labeled from 1 to n, so that's why we go up to n plus 1. And every time we see the in degree, if it's 0, then we will append I. Great. So now we have our sources. So from our sources, let me put it on the top. It'll be easier to see. Yeah, so from our sources now currently, we would have 1 and 2 on there. And then we have make a visited array. The reason why I want to make a visited array is because each time you have these edges, it's possible that a node has already been processed, so you don't want to put the neighbors on there again. Now we could perform our DFS where we go through the sources, and then we need an array for the next wave of sources, because each time we want to put all the new sources onto the array before proceeding, because that can all be done in one semester. And so as we are in the current semester, we go through every single thing in the source, and then we check to make sure we have not already visited this source. Because if we visited, then we don't put the neighbors. But if we didn't visit, then we go through the neighbors, and we see here, right? If we have 3 as the source, then the neighbors would be 1 and 2. Well, actually, that's slightly a bad example. What would be better is if we have yeah, what we have is actually 1, 3, and then 2, 3. And then 3 would be empty because, yeah, there's completing 3 doesn't complete any other prerequisite. So when we see that 3 has not been visited yet, then when we iterate the neighbor in edges source, we see we have 3. So the neighbor would be 3. And if we have not visited neighbor, so this so we're looking at 3. So if we haven't visited 3 and okay, well, I forgot one thing, which is if we haven't visited the source, then we can traverse the edge. And if we traverse the edge, that means the in degree, well, sorry, the in degree of the neighbor goes down by 1, so that should be here. This is edges, and then in degree. So when we're here, we see the neighbor of 1 is 3, and we haven't visited that yet. Yeah, so we haven't visited 3, and we decrement the in degree of the neighbor, which is 3 by 1. because we are traveling the edge 1, 3 by taking the course 1. And so one thing that could be special is 3 eventually it will have no integers. So we need to check that if the integer of the neighbor just became 0, then we would append that to the next source. It would be part of the next things we could take in the next semester. Now, after we process all the neighbors, then we're done with the current source, and so we could delete from the integer of source because there's no need for it. And then for visited source, we could set it equal to true, meaning that we've already visited this node, so we don't need to do it anymore. And then the next thing would be, since we finish all our sources, so the while loop would essentially terminate, but we need to process the next wave of sources. So source will equal next source. Yeah. So yeah, after we process, we would finish. This one would be removed, and then what else was on there was 2. So once we finish 2, or once we get to 2, right, we say, okay, have we visited 2? We have not visited 2. Oh, at this point, this is true because 1 has been visited, but 2 has not been visited. And then we look at the neighbor of 2, which is 3. And then we say, okay, we'll decrement the integer of 3 by 1. So now it's 0. And then we check, okay, have we visited 3? We have not visited 3. And then what's the integer of 3? Is it 0? And it is 0. So now we append that to next source. So now next source equals 3. And then we delete the integer of, we're deleting integer. Yeah. Okay. So deleting degree and then degree the edge. I deleted the edges on accident. So yeah, but anyways, at this point, we just have the integer of 3, 0. And then we mark visited as true for 2. And then yeah, if we continue in a similar fashion, then, well, we'll, yeah. If we continue in a similar fashion, then 3 will be processed. But the next thing is we have to plus equals 1 for semesters, plural. Yeah, so then sources, it's not empty. It gets assigned to next source. And the next source becomes 0, getting ready to process the next wave. And then, yeah, after we process the same thing for 3, it's pretty similar to 1 and 2, so I won't go through it. But then semesters will become 2, and then bam, that's the answer. Yeah, but we have some edge case to check, which is it's possible that, let's say I have a graph like this, it's called 1, 2, 3, and I also have another graph like this called 4, 5, 6. And so these will be processed with 2 semesters, but then this one, these will never get processed. And so that was the purpose of deleting from integers. Because if I see that there's, after I process these, and there's some graph that is cyclic, then the integers will remain in the integer hash map, and so, or dictionary. So then I would return -1 because it's not possible to take all the courses. So that's what this is for. All right, then we'll return to semesters, and that should be good. Well, yeah, a lot of talking in this problem. It's just, well, I don't know if it's a lot of talking. You guys can let me know in the comments, but yeah, let me just look through it to make sure it's solid. From collections, import default dict. That looks good. Then we make it edges, and the default dict is a list of all the classes where a specific course, after completing, will decrement all the integers. semesters is 0, and then in degree default dict is 0 because every node, before we build the graph, it doesn't have any in degrees. Then we go through the relations, and then the first element of the relation, that's the key. And then when we append, now we have the list of elements it is a prerequisite for, and then the in degree of the second element increases by 1 because element 0 of rel will be a prerequisite. And then we have sources, and every time the in degree is 0, we append the ith element. We have a visitor array to keep track of which neighbor if a source has been processed already, so we know which neighbors can be placed. Then we continue as source is not empty. And yeah, so next source, we need to keep track of the next wave of sources. And so we go through each of the sources. If it's not visited, then we go through the neighbors. Each time we decrement the neighbors by minus equal 1 because we're taking the current course. And then if the neighbor is not visited and the in degree is 0, then we append that neighbor because it's a new source, and then we delete this from in degree, delete the source from in degree because we're done, and we make sure that we show we visited by marking it with true. And then we change source equal to, no, it should be sources. So that was a typo that would have cost us. Make it equal to next source, semesters plus equal 1. And then this is the case where if we have a cyclic graph or cyclic graph plus this, it will catch that because we are unable to delete the in degrees since none of these have a source, so they can't be processed. So return -1, and then return the semesters. All right, let's check it out. Okay, so it looks like we have an indentation issue. So all this needs to be indented. All right, let's see what happens now. All right, cool. So this one looks good. That's this top example. Let's try out this second example to see if the in degree keys works. All right, great. Well, I could try out the one example I was saying where we have this 1, 2, 3, and then this is as 4, 5, 6. I understand it's a little confusing when I say that, but let me illustrate with an example. So with the 4, 5, 6, we would have 6 nodes. And so let's see, the mapping would be 1 becomes 4, 2 becomes 5, and 3 becomes 6. So basically I'm drawing this but as 4, 5, 6, and then this remains 1, 2, 3. So let's see if this catches. It should be -1. Yes, oh, excellent. All right, great. So it looks like runtime's pretty good. Whew, our memory is really good, better than less than 100%. Excellent. All right, so it looks like the runtime and space is pretty good. Let's talk about the runtime and space complexity for a little bit. So we are given n nodes, and then let's say we have e edges. So we need to iterate through each of the edges, and so that would be O of e time. And yeah, so that's right here. We have O of e time. And then we go through each of the nodes. So let's say we have v vertices, so that's O of v time. And then for sources, like our DFS, as we do our DFS, we are going through each source at a time. So essentially, the worst case is we go through all the nodes, so that would be O of v. But each time we are going through all the edges, so it's v times e. Every vertice has an edge. That would be the worst case. yeah, so runtime O of V times E. But I'm trying to think if I'm marking a vertex, I think each vertex only gets traversed once. But every vertex could have E edges. Yeah, it just means it could have like this course where it needs lots of prerequisites. But at most, it would be V. Yeah, so I would stick to the O of VE runtime. And then our space, we store all the edges and we store all the nodes. So it's O of V plus E. So overall, it looks pretty good. But yeah, let's see. There's some people that are more fast. And so I'll leave that up to you all. Yeah, please leave a comment below if you have code that's much more clean than this, and or even if you want to share your code, yeah, please share that. And if you think it'll help people learn, and if you have questions, please leave that in the comments below. And yeah, if you enjoyed this content, please like the video and subscribe for more, and follow me on social media. Hope you all have a wonderful day, and that each and every one of you learned as much and had as much fun as I did. And I'll catch you all in the next one.